Okay. I seem to be having issues with sharing my screen. I hope my audio is okay. Maybe in the meantime, I can look for a way that I can share my screen. So we start. Before I can get to know how to, maybe we can make use of audio. I'll make sure that I am as comprehensive as possible in terms of using audio, because I seem to be having issues with the screen. Okay, we had agreed that we are going to look at Form 3 work. We agreed that we are going to look at Form 3 work. So that means we are going to do some review of topics in Book 3. Today we are looking at probability. Maybe in the next sessions, we would receive or we would request that you give your suggestions to Mr. Mairura on what maybe you feel like should be looked into in the next sessions. So for today, like I've mentioned, we are going to look at probability. We are going to look at probability. I wish I was able to share screen, but we'll manage as I'm trying to struggle on sharing the screen. Probability, we start with the introductory bit, where in the introduction, we just do some brief definitions. And the first definition we are going to use is what is probability? Basically, what is probability? Maybe somebody from the class can tell us briefly what they understand by the term probability.
Chances.
Yeah, chances, we can talk about chances. So when you ask what is the probability that this event is going to take place, what they're asking you is, what are the chances that this event is going to take place? So probability just is a mathematical measure of chances. So when you talk about an event, occurrence, I believe those are terms that we've come across, so we know what they actually mean. Just a minute.
Denocar. Oh.
Kindly, Regan, mute your mic. Thank you. So as you wait for Mr. Mburu to come back, kindly you can be forwarding the areas that you feel you'd love us to review, so that we can prepare and have enough material for the same.
Okay, sorry for that. I had some issues to attend to. So you were saying that when you're asked to look for a probability, we are just requesting ourselves to come up with some measure of chances. We want to measure chances. What are the chances that an event is going to happen? Now we can measure chances from two maybe broad categories. One, we can measure chances if we are basing our measurement on theory. Then we have number two, when we are basing our measurement on some experiment we've carried out previously. So we can talk about two types of probabilities. That is theoretical probability. Number two, we can as well talk about experimental probability. So when you talk about theory, here we are basing our measurement or our tools of measurement on maybe an ideal situation. What would happen if we were not having any bias? What would happen if we are not having any bias? For example, if we tossed a coin, if we were to toss a coin, we are likely to get two outcomes. That is, we are likely to get a head or a tail. Theoretically, when we don't have any bias, we're supposed to have 50 chances of getting either sides. That is 1 out of 2 of getting a head or 1 out of 2 of getting a tail. I am still trying to see how I can share my screen, but let's proceed nevertheless. I'm hoping that my audio is okay.
Yes.
Okay, so as I'm trying maybe to see what I can do with my screen, I have some notes I would have wished to share, but I have issues sharing. Okay, now the other way that we base our measurement on is maybe an experiment we've carried out before. An experiment we've carried out before. And this experiment will inform the chances of an event happening. An experiment we've carried out before, which is likely to influence the chances of the next event. For example, when we are basing our argument on theory, we can have maybe a match. In this match, we have two teams. Possible outcomes would be team A winning, team B winning, and by team B winning means A losing or a draw. So we have three possible outcomes. So theoretically, if we were to base our measurement on chances, we would say that A winning would be 1 out of 3 because it's one chance out of 3 possible outcomes. Team B winning again would be 1 out of 3 possible outcomes because one chance favors winning of B and out of 3 possible outcomes. However, when you talk about now experimental, when you're talking about experimental, maybe the two teams had encounters before. And let's say they had played some 10 matches. And in these 10 matches, A had won 6. A had won 6. Maybe B had won 2. And we had 2 draws. Now, when you're playing the 11th match, we are not going to say that the probability of A winning is a third. It would have been a third if there was fairness and we were basing our argument on theory. However, here we had some previous encounters. In these previous encounters is what we are calling experiment. These previous encounters where A had won 6 is going to influence the outcome of the 11th match. So we will say that the probability of A winning the 11th match will be how many favors A winning? It is 6 out of the possible 10. So for such, we talk about experimental probability. The previous one, we've talked about theoretical probability because we are basing our argument on theory. What would ideally happen? What would be the idea or the most ideal situation? So here we assume that there is no biasness. But in the second one, we assume that there is biasness. A team is more likely to win than other. Just a minute, I see whether I am successful now in sharing. Okay, it seems to be giving me headaches. So that means we are going now to rely on maybe audio. So I will read out some examples. So what I expect from your end, because I cannot share, is that you're going to write maybe the examples down. Think through the examples. Then after you think about the examples, maybe you can say whether it is either theoretical or experimental. You write the example down, read through the example, suggest whether, or maybe see whether it is either theoretical or experimental. We have number one, a die is tossed once. What is the probability of getting a 1? A die is tossed once. What is the probability of getting a 1? A fair die is tossed once. What is the probability of getting 1? If a die is tossed once, what is the probability that you're getting 1 on top? Any suggestion? Any suggestion? Is the case there theoretical? Is it experimental?
Theoretical.
That is theoretical. That is true. That is theoretical because we are talking about a fair die. We are talking about a fair die. So the outcome is the ideal outcome. So we'll talk about 1 out of possible 6. It is 1 out of possible 6. Now I want you to compare that one with the following that I'm going to read. Write it down. We have a biased die which was cast and the probability number n showing up. So I read slowly. I believe you're writing. A biased die, so it's no longer fair, it's now biased. A biased die was cast and the probability of a number n showing up was recorded as, it was recorded as P into bracket n equals K into bracket n. I wish I was able to share my screen. Maybe moving forward, we will see of mechanics where we can maybe be sharing this. So we have P into n equals K into n. So we are talking about a biased die. So we are no longer talking about a fair one. P into n equals K into n. where K is a constant, where K is a constant. So find the value K and hence the probability of getting a 1. Find the value K, the probability of getting a 1. I don't know whether you've gotten that correct.
Please pardon, teacher.
Okay, I've said we have a biased die. A biased die was cast and the probability of a number n showing up was recorded as a biased die was cast once and the probability of a number n up was recorded as, so you write letter P, that is probability of n, open bracket, put n inside the bracket, equals a letter K, then you open a bracket, n.
So guys, I've shared something. Maybe are you in a position to see that? I've shared a screen. I don't know if you're in a position to see that. Maybe we can.
Yes, you
can see.
Yes, we can see that.
Here we can see.
So you.
Yes, Malimo, you can view it.
Mr. Mburu?
Yes,
Maybe
yeah.
You can use my. Okay, you can go ahead and use my. Let me delete this so that you can go ahead and use mine. Okay.
Whatever the teacher had written is exactly what I wanted us to have. So maybe Mr. Maria, you can put it again. From my end,
okay,
sharing
is,
seems to be a problem. So we have P into N.
You can also P into N.
Yeah, P is to N equals K into N. Yeah, that is exactly what I was talking about. Only that my screen seemed to be having issues. Okay, now that is what was recorded as the probability. The probability of having a number n is equals to a constant, then that number. So basically what we are saying here is the probability of having a 1, let that n may be any number between 1 and 6, because we are now talking about a die. A die has 6 faces. So the number n there is to give you the 6 different faces. So the probability of having a 1 is equals to some constant, then that 1. So the n will be from 1, 2, 3, 4, 5 up to 6. So the probability of having a 1 therefore is what? A constant, then 1. So question will be, is this case experimental or is it theoretical?
Experimental.
Definitely this is experimental. Why? Because there is some biasness. This K here is bringing out some aspect of bias. Theoretically or ideally, we would say the probability of having a 1 is 1 out of 6 because the probability that favors 1 is 1 out of 6 possible outcomes. However, this die is biased. Therefore, we have some constant there representing the bias. So where we now say, if you want to get a 1, it will be some bias times 1. So question, find the value of K. Find the value of K. I'm sure we've done such in class. So very fast, can we get the value of K? We have Ian Mayabi getting 1 out of 21. Maybe Ian, can you tell us maybe what you've done?
So Ian, you can write on the screen from your end, just pick the pencil and then guide us, take us through.
I'm not able to do that, but I just added all the probabilities of getting 1, 2, or 3, or 4, 5, and 6, then add all of them. You get 21k, and since you have, when you've added all of them, you have to get equals to 1. So 21k is equals to 1, k is equals to 1 over 21.
Okay, that is correct. What he's saying is, we have probability of getting a 1. So it is k times 1. Probability of getting a 2, k times 2. Probability of getting a 3, k times 3. So you go on like that up to the last outcome, which is probability of getting a 6. So you say 6 times k. And we know from a range of probability, probability ranges between 0 and 1. So all these should sum to 1. All these should sum to 1 because what we've just said, that probability ranges between 0 and 1. So therefore, make k the subject. So divide through by 21, you get that your k becomes 21. So what is the probability of getting a 1 therefore? Ukitaka probability of kupata 1, you say k, which is 1 out of 21, multiplied by 1. So the probability of getting a 1 is 1 out of 21. The probability of getting a 6. Maybe you can attempt that very fast. What is the probability of getting a 6 in this biased die?
6 over 21.
Itakuwa 6 out of
6 out of 21.
6 out of 21. That is the
So,
probability of
out of
getting a 6. Yes. Any question? So we've said that the probability of getting a 6, as it is being written there, it is k, which we got to be 1 over 21, into 6. So the probability of getting equals to k into n. Somebody is asking whether it is agreeable that you simplify. With probability, it's best you leave it unsimplified. Like if you have 6 out of 21, it is best you leave it unsimplified. 6 out of 21 will be okay. We'll see the essence or the need of not simplifying, especially when you're doing tree diagram. If you have like 6 event favoring and 6 out of 21, this means it is 6 out of possible 21. If you are to simplify this to give you maybe by 3, 2 by 3, 7, you'll have 2 out of 7. 6 out of 21 is not the same as 2 out of 7 when we are talking about probability. 6 out of 21 means what? You have 6 favoring out of 21 possible outcomes. So it is good you read it like you're reading an English thing. The other one is 2 out of possible 7. So 2 events out of possible 7s. So that means what? We have 7 events. I don't know whether that is clear. I'm saying
Yes.
6 out of 20 means what? We have 6 favoring out of 21 possible events. If you are to simplify 6 out of 21, you will get 2 out of 7. 2 out of 7, you read it like we have 2 events favoring 7 possible outcomes. So the denominator there gives you possible outcomes. 6 out of 21 is not in probability as 2 out of 7 because it is read out. It is read like 6 out of 21 possible outcomes. 2
Hello? Are we still there?
Yes.
Yes.
No.
Yes.
7 I have lost my network for a moment. I believe now you can get me.
Yes, you can.
Okay. Now, the next thing I want us to look at is combined events. Combined events. Now, for combined events, we have two types. Combined events, maybe, thank you, Mr. Mirura. Combined events. One, we can talk about mutually exclusive events. Mutually exclusive events. Then we compare that to independent events. Mutually exclusive events vis-a-vis combined, not combined, but independent events. Mutually exclusive events vis-a-vis independent events. Now, when you're talking about combined, we mean events that are happening together. These are just events that are happening together. And when they are happening together, or they have chances of happening together, they can be two tired. One, mutually exclusive. Mutually exclusive. And when we say mutually exclusive, there is a relationship in biology where we call mutual symbiosis. When we talk about mutual, whatever one is doing to the other one is also receiving the same thing from the other bit. Maybe we can have event A and event B. Event A excludes event B. Event A excludes event B. Event B also excludes event A. So in such a situation, we talk of mutual exclusion. A excludes B, B excludes A. A excludes B, B excludes A. So what do we mean by excludes? To exclude is just to prevent from happening, to prevent from happening. When A happens, it makes sure that B does not happen. When A happens, it makes sure that B does not happen. So that is to exclude. And when B happens, it makes sure that A does not happen. So we are seeing A blocking B from happening. B blocking A from happening. So they are excluding each other. A perfect example would be tossing of a coin. If you toss a coin, that is a fair coin, we are likely to have two possible outcomes, either H or T. H or T. When T is on top, H cannot be on top. When H is on top, T cannot be on top. So H excludes T and T excludes H. So we are talking about mutual exclusion. H excluding T, T excluding H. So there is mutual exclusion. One is excluding the other and the other is excluding the one. So that is mutual exclusion. I want us to be very careful about the understanding here. So that's why I'm stressing, because they become very important, especially when we are doing our tree diagram. Mutual exclusion. A makes sure that B does not happen. Happening of B makes sure that happening of A does not occur. Now, the other one is independent events. Independent events. These are events that will happen together and one does not in a way exclude the other. Maybe you can use an example. If we have a match being played, there is a possibility of A winning or B winning if we have two teams. If we have maybe two teams, we have three possible outcomes: a win, a draw, or a loss. A win, a draw, or a loss. If we have a win, maybe for one team, it will exclude the drawing and the losing. So the win excludes drawing and losing. A draw excludes winning and the other two possible outcomes. However, if you have two matches being played, team A and B are playing in one field, team C and D are playing in another field. The winning of A in field 1 does not block the winning of C in the field number 2. So the two are said to be independent events. The two are said to be independent events. The outcomes from the first field are mutually exclusive. However, comparing the two fields will have two independent events. The same thing with a coin. If we are to flip a coin twice, the first two possible outcomes, that is a head or a tail, are mutually exclusive. You flip a coin once. However, when you're flipping it for the second time, whatever we had in the first flipping does not block the outcome in the second flipping. So where we are having situations where an event is not blocking the other one from happening, we call that independent event. And when it does not block it from happening, we talk about event A and event B happening. As opposed to where we are talking about either H or T. So for mutually exclusive event, we use the word or. Maybe you can underline that we use the word or for mutually exclusive events. We get either a H or a tail. But for independent events, we talk about a head and a head. That is, you get a head in the first flipping and a head in the second flipping. So it is head and a head. You can get a head in the first flipping and a head in the second flipping. Okay, I believe that is all with regard to combined events. What you should know or what you should take is that for mutually exclusive, we use or, because one happen blocks the other. So we either take this or this. We can't take both. For independent events, it is this and this. It is A happening followed by B happening, or A not happening followed by B happening. So for independent events, we use and. For mutually exclusive events, we use or. Then I'm just doing a briefing because my notes failed me. The last thing that I want to look at before we look at now questions is a presentation of space. How do we present probability space? How do we present probability space? I wish my notes were showing, but we will work with what we have today. How do we present probability space? Now we have three various ways that we can present space. The first one, we've discussed this in class, is the tree diagram. You can write there, tree diagram. Then we can use a Venn diagram, although this is very common. A Venn diagram. Then there is what we call Punnett square, or just write a square. We can present our data in a square. P-double-N-E-T square. You can just say square. So this is a mathematical representation of space. So a question would arise then, what is a space? What is a probability space? When you talk about probability space, we are just saying what are all possible outcomes a list of outcomes. So when we talk about space, we are talking about list of outcomes. For example, if you toss a coin once, what are possible outcomes? You have H or T. So you want to present that either on a tree diagram or a Venn diagram or a square, what you're calling the Punnett square. Now, I want us to use maybe some examples, because with these examples, it will be best to know which method to use or to present our data. For example, if you have an example like this, maybe you can write it down. Write this example down. We have a class of 100 students. A class of 100 students. A class of 100 students, where we have 70 like mathematics.
Can't hear you.
Uh, 70 like mathematics, 60 like physics, and 40 like both. I hope you've captured that. 70 is for physics, 70 is for math, 60 is for physics, and 40 is for both. So we have both 10. Now you are told, find the probability that a student picked at random. Find the probability that a student picked at random. Find the probability that a student picked at random does not like either. Maybe, Norman, you can put your mic off.
Kindly put off the mic.
We put our microphones off unless you are asking a question.
Put your mics off, Eddie and Molly, or I can do that for you. Eddie and Molly, put your mics off. Molly, we are waiting for you. Thank you.
Okay, thank you. Now, here we've not been told how we are going to write down our space. We've not been told whether we are going to use a tree diagram, a square, or a Venn diagram. So it is upon you now to think which is the best way of representing this space. We are being asked to come up with the probability that if a student picked at random, he does not like either. Now, for such, where we have some interlocking scenarios, like we have a situation where a subject is being liked by both. We have 70 liking mathematics, 60 liking physics, and 40 liking both. If we have such an interlocking situation, the best to use is a Venn diagram. A Venn diagram where we say we have a rectangle. Maybe Mr. Marira, you can draw a rectangle in our board.
Yeah, I've done that, Mr. Mburu.
Okay, now in that rectangle, every student should fit in that rectangle. So the whole 100 students should be inside that rectangle. All the 100 students should be in that rectangle. Then inside that rectangle, we draw some circles. The first circle will be made up of students that like mathematics. Students that like mathematics. So we make a circle inside the rectangle that is going to incorporate students that like mathematics. Then we draw another circle that will be interlocking with the circle that we had previously drawn.
Yeah, so guys, kindly see that what I've drawn. What
Yes.
I've
So we
just
have
said.
I hope we are able to follow up. Are you following?
Yes.
Okay, I've started by saying we have a rectangle. In this rectangle is like the four walls of the class. Inside those four walls of the class, we should have the 100 students. Then we have the first circle, which is made up 70 that like mathematics. Then we draw an interlocking circle. We draw a circle that will be interlocking with the one that we had initially drawn, mathematics. So that one will be made up of students that like physics, and there are 60 of them. So this part where we are having some shared region, we did shared region in Form 2 when we draw some
So what
interlocking
I've just
circle.
stated. Yeah.
Now the shared bit there, you write 40. The shared bit there, you write 40. Why? Because 40 is for those students that love both the two subjects. So where we are interlocking the two circles, we write the shared population, that is 40. Now there is that other bit of the circle. And now we focus on the one for mathematics, where we are supposed to have 70. And note that I have started with 40, so that now the balance will be on the other bit where we have exclusively a region for maths. So they are supposed to be 70. So if I've already catered for 40, the balance that is 30 to be written on a region that is not shared. Then we are done with math. Now we go to that circle of physics. The circle of physics, we've already put or recorded 40. So our balance is, what is our balance? Somebody?
20.
20. Now the 20 you put in that region that is not shared. Remember there was that shared region where we put 40. So you put 20 on that bit of the circle that is not shared. Then if you are to add everything now inside 20. The circle, if you add everything inside the circles, what are you getting?
90.
Whatever you get at 4.
90.
You're having 90. And remember, this class was made up of 100.
Students.
Was made up with is made up of 100 students. So the balance 10 students. You can put it anywhere inside the triangle, or rather inside the rectangle, but not inside the circles. So that is 10. So the 10 you put it anywhere outside the circles, but within our rectangle. So what does this 10 that we have outside the circles, but within the rectangle represent?
Represents the students who don't like any of the subjects.
Yeah, that is the number of students who do not like either. So whatever we've done there is what we are calling a Venn diagram. Whatever you have there is a space representation using a Venn diagram. Although this one is not very, but it's good and simple. So if you have a situation where we are having events where we have some shared aspect or shared outcomes, this is best suited. So that now from here we can see students that like math alone are 30. So if you are asked what is the probability that a student picked at random like math alone, itakuwa 30 out of 100. Now, what is the probability that a student picked likes physics only from your Venn diagram? Anyone? It will be 20 out of 100. I hope all of us can see that.
Yeah.
That the probability of a student liking physics alone is 20 out of, because you're going just to take the 20 that is in the circle of physics and not in the shared part of our circles. The probability now, our question, that a student picked does not like either. So we are going to take the number of students that are within the rectangle but are not inside the two circles. So how many students do we have for such? How many students?
10.
So we have, so it will be 10 out of, it will be 10 out of 100. Okay, now that is in as far as the Venn diagram is concerned. Now let's look at the other way of representing space. Now we put our focus on the square, because that is now for the square it is common. It is not as the Venn diagram. So for square, this majorly is when we are combining maybe some outcomes. There are some outcomes that we are supposed to combine. And maybe the conventional example is when you are doing casting of dice. Let's say you are casting a die twice. So when you cast a die twice, we'll have some rows and columns. These rows and columns, I wish Mr. Madura would be able to do that, the sharing. We'll have some rows and some columns. And maybe in our first row, we put the space for the first casting, so that we have the space 1, 2, 3, 4, 5 up to 6. That is the first row. Then we leave some box there unused, so that in our first column, after we've left some box unused, we put the space for the second casting of the die. So we have some rows and some columns. Because we have 6 possible outcomes.
Cannot get you.
There is some square at the corner we left unused. So we use a 7 by 7 square. We use a 7 by 7 square, so that in the first row, we leave the first box unused. Then we use the other 1, 2, 3, 4, 5, 6. Then the column, we leave the first box unused. Then we have 1, 2, 3, 4, 5, 6.
Let me share another board.
I wish I had my notes working, but I believe the point is home. Are we getting what you are trying to say?
Yes.
Yeah.
Yeah.
We are using a square.
Yeah. No.
Are you getting my audio?
Yes.
Yeah.
So I was saying we are trying to represent the space in a square, and we are toasting a die twice. We have 6 possible outcomes, so we are going to represent our space in a 7 by 7 square. in a 7 by 7 square, so that the first corner square is left unused, so that in our first row column, in our first row, we write the space for the first casting, that is 1, 2, 3, 4, 5, 6. Assuming we are using a die. And in our first column, again, we leave the first box unused, so that we have 1, 2, 3, 4, 5, 6. So that now, whatever is left inside there, we are going to write down combinations of some events. So that if you get a 1 in the first tossing and a 1 in the second tossing, what you record inside the second column of the second row depends on now what the question will tell you. Sometimes the question will tell you to give sums of the two outcomes. Sometimes the question will tell you to give differences of the two outcomes. So it depends on how the question is going to be done. Sometimes they'll tell you to give sums, sometimes they tell you to give differences. I don't know whether Mr. Madura, you are fine sharing?
Yeah, I've shared what you've just said.
Okay.
About the square. I don't know if you are able to see. Guys, is the whiteboard okay? Are we able to see that?
Yes, the whiteboard is okay.
It's very okay.
Yes.
So whatever is creating there is a way of representing space or a way of representing outcomes, depending now on what the question is asking you to do. So row 1, kuna 1, 2, 3, 4, 5, 6. Hiyo ina represent nini? Possible outcomes of casting a fair die once. That is the first tossing. Column 1 in this other end, tuko na 1, 2, 3, 4, 5, 6. Hiyo inaonyesha nini? Possible outcomes of a fair die if it is cast now for the second time. Ile kwa row ya kwanza ni casting ya kwanza. Row ya pili, column ya kwanza ni the second casting. So kuna some other boxes that we've not used inside that square. Now these boxes will be filled in depending on how the question is. Sometimes the question will tell you, find the probability that the sum is 2. So what is it telling you? You're supposed to get the sum of the two outcomes. For example, if I were to cast the die the first time, inipe a 1. Alafu, in the second tossing, bado inipe a 1. So the sum here will be 2. So the first empty box there will be filled by 2. These 2 came from the sum of the 2. So the question is directing me to fill in my space, my probability space, my possible outcome by getting sums of the independent or the individual casting. Hivyo iko sawa?
Yes.
So that now in the farthest lower, we can have a 6 and a 6, so that it will be 6 plus 6 to give me a 36. So that's how we fill in that space. A space which we've defined as a list of possible outcomes. A list of possible. Maybe you can do one on your own where we are now getting difference. For example, the probability of getting a difference 2, the probability of getting a difference that is less than 2. You can do that maybe on your own and maybe see how it will come out. See how the outcome will be. Now, another example that we can use the Punnett square is maybe when you're told Maybe you can write this down. Say that a two-digit number is made up of the first four composite numbers. A two-digit number is made up of any of the first four composite numbers. Maybe you can even say irrespective of the order. It is made up of the first four composite numbers, irrespective of the order. Write down the space. Write down the space, or write down any possible outcome for such a description. We have a two-digit number that is made up of the first four composite numbers. So write down a space for that description. So again, here we are combining two numbers because we are talking two-digit numbers. We are making a combination of two numbers. So the best method of representing this space however, you are required to pair up some number.
Excuse me, sir, I can't hear you. Oh, we can't hear you.
We can't hear you.
We can't hear you.
Oh, we can't hear you.
So candidates, be patient. Maybe is experiencing some issues with its network. So first of all, you need to understand what composite numbers are before you respond to that question. You need to know the type of consecutive composite numbers before you respond to that question. So anybody can share with us what composite numbers are?
Composite numbers
Wait
are
for
opposite
Mr. Mburu.
of prime numbers.
Opposite
Sorry?
of prime number.
Yeah, opposite of prime numbers. So in short, numbers with more than two
One
factors.
factor.
So I'm sure with, yeah, numbers with more than one factor, not two, sorry. So I'm sure with that we can now be able to respond to that question. So you can go ahead and work it out. And then once you are done, I can, so using this whiteboard, I'm sure you can write, one person can write from their end. And then maybe you just let us see what you've done.
Okay, I hope my audio is back. For some reason, I had lost my network.
Yes, it's back.
Okay, now I was saying before my network went down that anytime you are told to combine some two events, like you are pairing up some numbers, you are pairing up some.
Attention, class.
Thank you very much for standing by. But I was thinking as Mwalim gets back, we can do a quick roll call, just like we were doing the other day. So look on your screen, you will see your class. Just pick your class.
Anybody can share with us what composite numbers are. Yeah, opposite of prime number. So it's got numbers with more than, numbers with more than 2%. So I'm sure with, yeah, numbers.
Are you getting me?
Yes.
Yes.
Okay.
Yes.
I believe Mr. Mariro had briefed you on what a composite number is. And as we were doing that, so maybe we can list them. The first four composite number would be made up of maybe 2. We have a 4. The next one would be
6.
6, then followed by
8.
Then 8. So those are the first 4 composite numbers. Now these are the digits that are going to come up with the number. Remember, a number is made up of digits. We are told that it is a 2-digit number. We are creating some 2-digit number, and the numbers that we are going to use, or rather the digits that we are going to use are, Charles, you have a question?
Yes.
Is composite number.
We say that composite numbers are the opposite of prime numbers, and you have written 2, and 2 is a prime number.
Maybe a composite number is that any number that has more than one factors, like 1, 2. That is a composite number. 4, it has 1, 2, yenye iko na zaidi ya moja, basically. Okay.
But 2 has 1.
2 has 1 and 2.
No, sir.
Excuse me, Mwalim. I think composite numbers are numbers which have one.
Which has?
Which has more than 2 factors.
More than 2 factors? So it takes
prime numbers have 2 factors.
Maybe.
So we can start with 4.
Maybe for the purposes of demonstration, let's start 4, 6, 8, then 9. But in the meantime, we can check whether 2 is a composite number. Maybe we can look at what is the definition of composite number. But for the purposes of this class demonstration, let's use 4, 6, 8, and 9. Okay. But later on, we can check whether 2 is actually a composite number. But for the purposes of demonstration, let's use 4, 6, 8, and 9. Okay. Now we want to combine this. We want to combine these digits so that they come up with numbers. So for example, we can have 46. 46 is a 2-digit number. It is made up of 4 and 6. We can have 48. 48 is a 2-digit number, which is made up of 4 and 8. We can have 49. But now instead of saying we can have, it is good we come up with a square that will, in a neat way, give us the whole space. We can come up with a square that in a neat way and in a comprehensive manner, give us the whole space. So like we did with the case of die, we can have the first row having 4, 6, 8, and 9. Then we have the first box unused there. Because we have 4 possible outcomes, we use a 5 by 5 square. We use a 5 by 5 square. The first box is left unused. So that the second box, that is the second column, we have 4, 6, 8, 9 to make a row. Then in our first column, we focus now on the first column. We leave the first box unused so that now we have 4, 6, 8, 9 down the column. So inside the square, we will have now the combination of the two. We'll have a square inside there where now we combine the two. Maybe we can start with row 2, which has a 4 in column 1. So tuchukue hiyo 4 na 4, alafu 4, 6, 4, 8, 4, 9. Tuko sawa hivyo? Are we together?
Yes, sir.
Okay. Now, the second one will be a 6 and a 4. A 6, combine it with a 6. A 6, combine it with a 8. A 6, combine it with a 9. Then the next one, 8, combine it with a 4. 8, combine it with a 6. 8, combine it with a 8. Then 8 and a 9. Lastly, we have 9 and a 4. 9 and a 6. 9 and a 8. Then lastly, 9 and a 9. So what we are saying is, in a situation where you are told to combine some numbers, maybe you are combining outcomes from a die, you are coming up with a 2-digit number where you're supposed to combine a digit and a digit. In such scenarios, use a square. If you have 4 numbers or 4 possible outcomes, create a 5 by 5 square, so that in the first row, you leave the first box unused, list down your outcomes. In the first column, leave the first box unused again, list down your possible outcomes if it was fair. Then inside the unfilled in squares, do what the question is wanting you to do. If the question wants you to get sums, get the sums of row, column, row, column, row, column. If the question wants you to get product, again, go ahead and do product and fill in the empty boxes there with the product. If it's like this question that we've just done, where you are coming up with a number that is made up of these digits, make sure you match them. Take row 1, combine with all the columns. Take row 2, combine with all the columns, like that up to the end. Then from whatever we have here, you can be asked any probability question. For example, you can be asked, find the probability that the number formed is a prime number. Find the probability that the number formed is a prime number. Maybe somebody can help us get that.
Excuse me, Mwalimu, before we go on. Yes.
Yes.
In this question, we were told irrespective of the order, shouldn't we have some boxes having 2 numbers? For instance, where we have row 6, column 4, should we have 64 and 46? Should we also list 46 there?
We have 64 and 46. Do we count that as 1? Maybe 64, 46. Is it the same number? Because we were told irrespective of the order. Do we count it as the same number? Maybe what I can say is for us to come up with the space, it is best we respect the order. That is my view. I don't know what your view would have been. For us to have the perfect space. Because a 46 and a 64, those are 2 different numbers. That's my thinking. Okay, if there is no any idea, any additional thing on what Madam has asked, we are told not to respect the order, but we want to come up with a space, and in this space we must include all the possible outcomes. Remember, for space we are talking about all possible outcomes. So she's saying we have a 46 and we have a 64. Do we count those as two different outcomes? Do we combine them as one outcome? But my thinking would be those are two possible, two different outcomes. Kigen, Frederick.
To my view, I think when the question said irrespective of the order, I don't think it's the concerning the interchanging of the numbers. For example, what Madama said, 64 and 46. I think it was concerning the order of, for example, or do we have arranged 4, 6, 8, and 9, the order of the composite numbers that you have arranged. So I think the numbers should still be all arranged well, but now the order shouldn't be exactly from 4 to 9. It can be 9 to 4, of which with that arrangement is still going to give us the same numbers you have outlined here.
And now the last, I hope my audio is clear.
Yes.
Yeah, somebody is saying that
Yes.
there comes. I tend to believe so, because 46 under 64. That is my. But we can maybe jog our minds and think about what she is asking. Okay, the last one, and now this is the most common and the simplest, is a tree diagram. And the most common, really tested, and the easiest maybe to use in coming up with a space is a tree diagram. Now, for a tree diagram, we go back to where we started. We talked about dependent events compared to mutually exclusive events. Now, this is where those concepts are needed most to distinguish an independent event from a mutually exclusive scenario. Why am I saying so? Because for every branch you create, you must record a mutually exclusive event for every branch. From one level of a tree diagram to another, that's where now we put independent events. For every branch you create, you record mutually exclusive events. So at no point should you record independent event from the same branch. They should not emanate from one point if they're independent event. So as you are drawing your tree diagram, make sure you are able to distinguish the two. If we are talking about an independent event or a situation where events are independent, do not draw them from the same point. For example, if you toss a coin once, the outcomes will be H or T. So H or T should emanate from one point. Mairura, are you there?
Yeah, I'm here. I'm Mburu.
So we start from a point 0. We start from a point 0, then we create a branch. So we start from 0, create a branch. Then in one end of the branch, we put the first possible outcome. We can say H. Then the other bit of the branch, we put T. So the interpretation is we are toasting, we're having a one coin toasted or toasted or toast. So the outcome will be what? H or T. And I'm stressing on the word or. We are either using the first root or the second root, either going towards H or T. So make sure you stress on this word or. That is branch from a tree diagram. So that now if we do the second tossing of the coin, whatever we recorded on the first one does not influence what we are going to do in the second. It may influence in some cases, but it will not block. The word is to block. Or it does not exclude the second event. So if we had taken H in the first tossing, going to the second tossing, now we extend our branch from the first H. We create another branch there from H. Then we record H and T. So the interpretation here is what? We started from the first tossing. We tossed the first coin. It gave us a head. In the second tossing, we are going to get again H or T. Second tossing, H or T is mutually exclusive. So we are only creating a branch for mutually exclusive events. Haya, kwa hii T ya hapa chini, again, we create another branch. The outcome will be H or T. It is H or T. And again, stress on the word or, because these are, you either get H or T. Now, after that, we create our space now immediately after we are done with the tree here. So that here we have H and H. H, H. The stress is on the word and. I. Remember when we are starting, we said for events we use the word and. The H we got in the first tossing is dependent on the H we are going to get in the second tossing. Whatever we did in the first case may not or does not influence whatever we are doing in the second tossing. So that's why we have H and H. It is ahead followed by ahead. Now, in the second, we have H and T. H and T. Again, the stress is on the word and. Why? It is ahead in the first tossing and a tail in the second tossing. Here we are having independent events. From one level to another in a tree diagram, we have independent event. It is a head followed by a tail. Then we have a tail followed by a head. These are again a combination of two independent events. We got a tail, then we got a head. They are independent. They are not in any way linked. Compare that with what we had in the first tossing. It was a head or a tail. A head or a tail. One level to another, that is the first tossing compared to the next tossing, a head and a head. A head and a tail and a head, a tail and a tail. So as you're moving along a tree diagram, we have independent events. Very important. As you're moving along a tree diagram, we have independent events. As we are branching in any branch of a tree diagram, we have mutually exclusive events. As we are branching any branch of a tree diagram, we record mutually exclusive events. And maybe something to give you a hint on, every mutually exclusive event, if you add the outcomes, you normally get one. John Gisore. John Gisore, your hand is up. Okay. And maybe we can have an example that will help us understand what we are saying. We have 3 people. Write this down. We can talk of maybe Joel, Susan, and maybe Koech. We have Joel, Susan, Koech. They are practicing archery. We have Joel, Susan, Koech. They are practicing archery. The probability that Joel hits bullseye is 1 out of 6. The probability that Joel hits bullseye is 1 out of 6. The probability that Susan hits bullseye is 2 out of 5. The probability that Susan hits bullseye is 2 out of 5. The probability that Koech hits bullseye is, let's say, 1 out of 4. So we have Joel, Susan, and Koech. 1 out of 6, 2 out of 5, 1 out of 4, respectively. You are told represent the following information on a tree diagram. So Kiambua represent the following information on a tree diagram. They are telling you to create possible outcomes. In other words, they are telling you to come up with the space. List down all the space, but now you use a tree diagram. Now here, we've said what? If it is mutually exclusive, that is the only time you create a branch. If it is independent, you move from one level of a branch to another. So we only create a branch for mutually exclusive events. We only create a branch for mutually exclusive events. If they are independent events, they should be one level of a tree diagram to another, not emanating from the same point. They should not emanate from the same point if they're independent. Now, the chances of Joel hitting, Susan hitting, Koech hitting are independent. Whatever Joel does has nothing to do with whatever Susan does, so they're independent. So that tells you, when you're creating the tree diagram, you should never have the 3 names emanating from one. That is a mistake a majority of us do. When we are told to create a tree diagram, where we say JSK to emanate from one point, that is very incorrect, because we've said every branch should emanate, or rather, any branch should record mutually exclusive events. Any branch should only have mutually exclusive events, so that when you move from one level to another, that's when you record independent events. So briefly, we can have that. So how do we go about this case then? Maybe somebody to just tell us very fast how, because of time, how do we go about this case? We have Joel, Susan, Koech. We've noted that they are not mutually exclusive. They're independent. So how do we go about such? Come on. How do we record that on a tree diagram? Anyone very fast because of time, so that we can wind up? Yes.
We can start with Joel's probability of hitting bullseye and not hitting bullseye. Then from those 2 probabilities, which do not affect Susan's probability of hitting or not hitting bullseye, then we can go to Susan's probability of hitting or not hitting bullseye. and then to correct.
Yeah, that is perfect. Like we've said, a branch should only have usually one event. So if we record Joel hitting, the event that excludes that is Joel not hitting. That is very perfect. If we start with Joel hitting, the event that excludes Joel hitting would be Joel not hitting. So from our branch, we have Joel hitting, Joel not hitting. So if Joel hit, we go to Susan. Susan will hit. If Joel does not hit, we have Susan hitting, Susan not hitting. Then finally, we'll have Koech hitting, Koech not hitting. Like that. Any question so that we can finish up? Any question, any concern? I would advise that we look at the questions in KM before we can have the next meeting, which I believe I'll be able to share my notes in a way that will be making the lesson more ahead time, just depending on video only. But I believe we've learned something.
Yes.
Okay.
Yes. Thank you.
Okay, so next lesson, we are going to make sure that we incorporate better sharing of screen and better sharing of notes. I was saying, I advise that you look at questions from KMF, look at varied questions, especially questions that require you not just to over rely on the tree diagram. Look at those questions that will want you to use the square, those that will may want you to use the Venn diagrams and such. Otherwise, thank you very much. See you in the next lesson.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Thank you for the lesson.
Nigga.
Library.
Isaac Mogira, your hand is up.
Hello.